We don't rise to the level of our expectations, we fall to the level of our training. Hi guys, welcome to lesson 4 of Finance and Recursion. Now, this quote is one of my favorite quotes. It sort of reminds me that I should be doing something when I'm doing nothing. But it also, you should remember that you can always congratulate yourself on the little things that you do for yourself. The things that make yourself just that little bit better than you were yesterday. It really makes all the difference. It's probably a good reminder in times like these where it is pretty easy to spend a day just relaxing and watching Netflix and doing whatever, but doing just that little tiny bit is so much better than doing nothing at all. Without further delay, let's get into the lesson. So, today's lesson is modeling geometric growth and decay. So we did linear all of the last 3 lessons. Now we're looking at geometric. And our goal is to model and analyze growth and decay in financial contexts using a first order linear recurrence relation. Okay, what's this? First order. All this is the fact that we're only using, now ignore this R for now, I'll explain that in a bit. We're only using Vn and Vn plus 1. For an example of a second order recurrence relation is the Fibonacci sequence. So Vn plus 2 equals Vn plus 1 plus Vn. Remember that Fibonacci sequence? It's just the sum of the 2 previous numbers. That's a second order recurrence relation. We only, in further maths, really deal with first order recurrence relations, especially in the finance topic. Anyway, let's have a look at this example. Because just to make sure that we're all over the difference between unit cost and flat rate depreciation, let's have a look at Ken's caravan. So Ken's first caravan had a purchase price of 38 grand. After 8 years, the value of the caravan was 16,000. So remember, this is scrap value, this is V0, this is N. The caravan has traveled an average of 5,000 Ks in each of the 8 years since it was purchased. Oh, okay. So this is a bit interesting, a bit of a mix of N, number of years, and unit cost. Assume that the value of the caravan has been depreciated using the unit cost method. Okay, unit cost method. By how much is the value of the caravan reduced per kilometre travelled? Well, how we do this is we start off with figuring out the difference between the initial value and the scrap value, which is 22,000. Then we divide that by the number of years. And some people might want to do this step, combine these next 2 steps, but we'll separate them. Divided by the number of years to figure out how much it depreciates by each year, 2,750. Then you divide this, the amount depreciated per year, by the amount of Ks per year. Remember that this 5,000 is 5,000 Ks driven in each of the 8 years. This ends up being 55 cents per kilometre. So every kilometre that this caravan's driven, it depreciates by 55 cents. So that's a good example combining both flat rate and unit cost depreciation. All right, for those of you that are happy with just equations, this is what I've done. I've put the equations for this lesson in this slide, so you can just go straight to 5D on a Drolo if you want. Now, this thing here is our recurrence relation. Remember that we need an initial value and something that's telling us what to do each time. Here we've got our next value is equal to some factor, and we'll call this the compounding factor. It's either going to be compound interest or reducing balance depreciation. So those are our 2 finance examples. That value times the previous value. So remember, for the last few lessons, we've looked at something that has a plus d or a minus d. Now we're multiplying by the same amount each time. This capital R is equal to 1 plus or minus, so compound interest or reducing balance depreciation, R, which is the rate, over 100. So you guys should be going to your notes page, and you should be doing something like this right about now. Compound interest, recurrence relation, V0 equals principal, Vn plus 1 equals that, reducing balance depreciation, recurrence relation equals starting value, RVN, R1 minus R over 100. So write those notes down into your notes, into your columns, which is the way that we're setting up Recursion and Finance. Write those notes now. Please pause if you need to. I'm going to keep going. Alright, so for geometric growth and decay, it can be seen in compound interest and reducing balance depreciation. So geometric growth or decay is in a sequence occurs when quantities increase or decrease by the same percentage at regular intervals. So for simple interest and unit cost depreciation, as well as flat rate depreciation, you added the same amount, not the same percentage. You added the same amount each time. So it was changing by 50 each time, for example. In this case, we're changing by the same percentage, which means the amount that we're changing by might actually change each time, or it should change each time. An example of this would be a recurrence relation where you had a starting value of 1, and then your rule was to multiply by 3. So your next value is 3 times your previous value. 139, so on, so on. And you can see here, we've got a bit of a curved pattern. Another example where you have decay is starting value of 8. Your next value is equal to half of your previous value. Rule is multiply by 0.5, 842. Now we're decreasing. So this is the difference between geometric growth and linear growth. Linear growth, you've got a straight line. Geometric, you've got a curved line. Now this is the picture that I've put into our notes to compare arithmetic, or same as flat rate, or simple interest, those kind of words. That's what we're talking about when we're talking about arithmetic growth, and geometric growth, where you've got a curved line. So those are the differences. I've put this picture up here as a reminder to show the differences. But yeah, arithmetic, our other word for that is linear. All right, for compound interest, V0 is our principal, Vn plus 1 is R times Vn. Vn plus 1 is the amount of the investment, one time period after Vn. Capital R is the growth or compounding factor, 1 plus R, little r, over 100, where little r is the interest rate per compound period. When R is greater than 1, you have geometric growth. When R is less than 1, you have geometric decay. So geometric decay is not actually compound interest, it's actually reducing balance depreciation. And we'll look at an example of that in a bit. So this is a table of values of compound interest. Your starting value is 1,000. You add 12% interest. So in this case, our little r is 12, which means our large R is 1 plus 12 over 100, which is 1.12. Now 12% of 1,000 is 120. You add 1,000 plus 120, you get 1,120. And you put that value in, you find 12% of that, and then you add that on, and you keep finding 12% of that previous value and adding it on. So that's what we're talking about with compound interest. That's right, you're not adding 120 each time. It's actually the amount that you're adding each time grows each time. Now, for reducing balance, each year or time period, the value will be reduced by a certain percentage of the previous year or different time period's value. Here, R is 1 minus little r on 100. Let's look at some examples. The following recurrence relation can be used to model a compound interest investment of $2,000, paying interest at the rate of 7.5% per annum. V0 is 2,000, Vn plus 1 equals 1.075 times Vn. In the recurrence relation, Vn is the value of the investment after n years, so we're just making that explicit there. Use the recurrence relation to find the value of the investment after 1, 2, and 3 years. Okay, so we're starting with 2,000, so that's after 0 years. So after 1 year, so V1 equals 1.075 times 2,000, because our previous value before V1 was V0. That is equal to 2150, just looking at my cheat sheet here. V2 is 1.075 times 2150, which is $23.25. V3 is, you do the same thing again, but you're putting this new value in, and that is equal to $2,484.59. So if a question asks for the value after 1, 2, and 3 years, or like each of the next 3 years, you do have to write every value out. So you do have to do this by hand, write every value out. Determine when the value of the investment will first exceed $2,500. Well, let's go to our CAS, and what do we do for this one? We write our starting value of 2,000, and then we know that we're multiplying by 7.5%, so we're going to go times, and then in brackets I want you to put 1 plus 7.5 over, and you guys might want to put this instead so it's a bit more clear for you, over 100. So you're multiplying it by 1 plus 7.5 over 100. So we get 2150 as we knew. Now we've got this other value. Remember what happens when we go here, when we get fractions, we want our calculation mode to be approximate. So next time I press enter, we now have $2,484.59. So just as we had before, we're looking for when this first goes over 2,500. We've pressed the enter key 4 times now, which means this is V4. So it's not over 2,500 in V3, but it is in V4. So the answer is 4th year. Yeah, or in the 4th year. Now, write down the recurrence relation if $1,500 was invested at a compound interest rate of 6.0% per annum. Okay, so recurrence relations always need a V0, sorry, 1,500, and our Vn plus 1 is equal to our, we know it's going to be R times Vn. Let's calculate R over here. R equals 1 plus, what's our rate? Our rate is 6.0 over 100, which is 1.06. So this is going to be 1.06 times Vn. And that's it for our recurrence relation. All right, what about Brian? He's borrowing $5,000 from a bank. He will pay interest at a rate of 4.5% per annum. Let Vn be the value of the loan after n compounding periods. Write down a recurrence relation to model the value of Brian's loan if interest is compounded yearly. Okay, V0 is 5,000. This should be your automatic step by now. Vn plus 1 equals, well, let's see what R is equal to. 1 plus, what's the rate? 4.5 over 100, which is 1.045. Okay, 1.045 times Vn. That's our recurrence relation for yearly compounding. What about quarterly? This is where things are a little different. Our V0 is still the same, it's still 5,000, but we need to calculate a value of R that's a little different, because little r is now 4.5 divided by 4, because we're now compounding quarterly. So 4.5 divided by 4 is equal to, let's look at my cheat sheet, 1.1125. Sorry, that's wrong. 1.125. Now, this means our capital R is equal to 1 plus 1.125 over 100, which is 1125. Whoops, not my best day. So Vn plus 1 equals 1.01125 times Vn. So keep in mind that our little r changes when we're looking at different compounding periods. So that's really important. For quarterly, we divide that by 4. For monthly, I think you guys can guess what we're dividing by, unless you don't know how many months are in a year, in which case please learn that. All right, our R is equal to now 4.5 divided by 12. There's 12 months in a year. And that is equal to, let's look at my cheat sheet, 0.375. Which means our capital R is equal to 1 plus 0.375 divided by 100, which is 1.00375. So Vn plus 1 equals 1.00375 times Vn. Cool, we're making progress. So this is how we deal with compounding periods which aren't just your basic year. We have to divide by the number of periods there are in a year. All right, let's look at this example for reducing balance depreciation. The following recurrence relation can be used to model the value of office furniture with a purchase price of $6,900. Okay, V0 is 6,900, makes sense. Vn plus 1 equals 0.93 times Vn. What does this 0.93 mean? We can calculate the depreciation rate from that. We can see 0.93 is, if you know your decimals and percentages well, you can see straight away that that's 7% lower than 100%. So the depreciation rate is 7%. Now, how do I figure that out? Well, I can do this as well. I can do 1 minus 0.93 and then times that all by 100, and that will give me 7. That'll also tell you what the depreciation rate is. But whatever way you do it, make sure that it works and then keep using that way. You don't have to use this way. You don't have to use anyone's way. Do it your way as long as it works. Now, in the recurrence relation, Vn is the value of the office furniture after n years. Use the recurrence relation to find the value of office furniture correct to the nearest cent after 1, 2, and 3 years. All right, I'm just going to flip my cheat sheet. So we know V0 is 6,900. It's a good thing to write that down sometimes. V1 is equal to 0.93 times 6,900. So the previous value, and this is equal to 6,417. V2 is equal to 0.93 times this value, so 6,417, which is $5,967.81, and V3 is 0.93 times this value now, $5,967.81, which is $5,550.06. Now, something I should have alerted you guys to before, but we are always rounding to 2 decimal places because we're dealing with money, which gets always rounded to the nearest cent. And then finally, the last example that we need to talk about: determine when the value of the investment will be first less than $5,000. Well, what's our starting value? 6,900. And this is something that we'll actually do in our CAS. So 6,900 times 0.93. We know it's 0.93 from the recurrence relation from the previous page, so I'll just go that. Double check. Yes, it is 0.93 times the previous value. So actually, we have to start with 6,900, enter. Then 6,900, whoop, and we go times 0.93. And we're looking for the first time that it's below 5,000. So that's 1, 2, 3, 4. Okay, so after the 5th year, it's worth less than 5,000. So after 5th year is the answer to that. Finally, write down the recurrence relation if the furniture was initially valued at 7,500, so we should write here V0 is that, and then depreciating at a reducing balance rate of 8.4% per annum, so R is that. Let's write down the recurrence relation. Okay, we know a recurrence relation always starts with V0, and we can just write that down. And we know that the next line of our recurrence relation always has Vn plus 1. Now, we know we're looking at reducing balance, so we have to calculate an R, capital R. And this is going to be 1 minus, because it's reducing balance, 1 minus 8.4 over 100. Remember, little r over 100, which ends up being 0.916. And therefore, our recurrence relation is 0.916 times Vn. Alright guys, that's all you need to know for doing today's work. It's a Drolo 5D, those questions, so skip question 1 and 6 it looks like. If you have any questions, please send them to me in Microsoft Teams or send me an email, however you prefer. And yeah, good luck.